NuScale steam generator is a huge machine. 1,500 tubes. How many weldings on this? How reliable is such machine? You cannot put the NuScale machine or something else on the barge or vessel. It's a huge. Each core can be calculated for the one parameter, equalized by one parameter. It's a power density. If your power density is small, you need a big core to get same power. If you make a big core, you making the big vessel, you making big biological shielding, you making big reactor compartment, you making big reactor protective shell or something like this. You gotta build huge machine.
A warm welcome back to Decouple. Today I'm joined by Aleksey Rezvoi. Aleksey is a naval and maritime nuclear propulsion expert, originally from Russia, now living in the United States, with a long and illustrious career in the sector. Today we're going to be chatting about maritime nuclear applications, particularly nuclear cargo, which has risen to prominence due to interest from organizations like international maritime organizations in decarbonization. Before we dig deeper in, Aleksey, I'd like to give you a better chance to introduce yourself. That was very bare bones. I've poured over your LinkedIn profile, but you have a long and storied career. So tell us a little bit about your background.
Okay, hello everybody. And short introduction. I graduated in 1986 as a naval mechanical engineer with specialty of nuclear power propulsion for submarines and icebreakers, and used to work on the Russian Soviet naval program with test facility of generation 3 and generation 4 of Russian reactors, submarine and icebreakers reactors. Immigrated to United States, get my second degree in the nuclear engineering in Texas A&M, and pursuing PhD right now. And all my life, it's pretty much close to 40 years. I'm used to work on the, some projects related to the small reactors or maritime reactors, except several times when I used to work for the conventional nuclear power plants. And collected some skills, knowledge, experience in this area, and working right now as a consultant mostly.
So I've had my interest really tweaked in my I guess geopolitical interest in the northern sea route, which is the sea route which goes along the Russian Siberian coast and connects Europe and Asian markets about 12 days faster than an analogous trip through the Suez, or an even longer trip around the Cape of Africa in the context of Yemeni rocketry fire in the Red Sea. And this led to a real fascination just by beginning to understand the scope and scale of what has happened so far in the Russian civilian nuclear maritime propulsion world, and what is underway. Just last week, there was an announcement about something that sounds utterly science fiction, but a nuclear-powered LNG submarine, I guess, to ply the waters of the northern sea route. So some things sound like science fiction. We also have some real examples. The academic Lomonosov, a floating nuclear power plant in Pevek in Chukotka, which is taking over from the world's northernmost nuclear power plant, Bilibino, which is being decommissioned. I think there's 1 or 2 units still in operation. Suffice to say, there's a lot happening on that northern sea route, which again is kept open throughout some of the winter and fall months by nuclear-powered icebreakers. It's a real kind of center in the world for activity in this sector, and there's a lot of talk, a lot of flapping lips in the West right now with I think grandiose plans of decarbonizing shipping more broadly with nuclear reactors. We have organizations like Core Power. We have pilot studies by the Lloyd's Register, by the International Maritime Organization, starting to look at this question of how could we decarbonize shipping, and we have a history of nuclear-powered cargo ships like the NS Savannah and some other examples. But again, I guess I'm fascinated and interested to talk with you, Aleksey, because you have a lifetime of experience in both worlds, bridging the Russian world and the Western world now. And your formation was really in maritime nuclear propulsion, again, in an environment in which, again, there have been a whole fleet of nuclear icebreakers, for instance, deployed. So today's conversation, we're not going to be chatting so much about nuclear submarines and aircraft carriers, where I think there's a really strong rationale for their development and special use cases, but now looking at some of the edge cases into nuclear transportation in the form of cargo ships. So maybe we could start just by getting a sense of again your early formation as a professional in this sector. I want to get a sense of the sort of infrastructure within the Russian state to support something like its icebreaker program, the design bureaus, the facilities, because I think that's something that gets overlooked a lot when we start talking about and fantasizing in the West about the idea of nuclear cargo shipping. There's a lot of infrastructure, human resources that are required to make a program work. So perhaps you could start by giving us a bit of a bird's eye view of what that program looked like in Russia when you were there. What sort of human factors and infrastructure required, say, to design, build, operate, and deploy icebreakers in the Northern Sea route?
Well, first of all, yesterday I saw the news. The first Chinese container ships vessel passed through the Northern Sea path and in 20 days to and reach the Rotterdam. I don't remember. It's just 20 days compared to 40 days across. It's a different way. Of course, it's a part of decarbonizing. If like spending twice more time, like you using twice more fuel. Anyway, the if you see Russian map, you can see a lot of northern territory in Arctic, same like in Canada, for example, and a lot of minerals, a lot of oil, gas located in this area, and we understand, you know, uh, the human cannot live without this energy next several decades, and it's required to take these minerals and oil and gas from this area. This is the reason I call this, like national reason to develop the small nuclear um, reactors. It's not just because we want to do this, and just because it's required for Russia. Maybe same parallel we can say about like we making maybe we can make parallel with Canada, for example. It's it's pretty much same situation and remote access to the energy for small cities, small towns on the north. Now, part of the story is, like this program starts in the Soviet era from the first icebreaker Lenin. And by the way, my father used to work on this icebreaker on the shipyard. And right now, Russia has a significant fleet of icebreakers and significant, probably best in the world. Know that experience in the like around the maritime program. How it happened, as I mentioned a little bit in my presentation, when I presented myself, I used to work for the fourth and third generation Russian nuclear submarine reactor. Which means, like first icebreaker used the generation one nuclear reactor, same like on the nuclear submarines, and was rebuilt and removed on some time and put and on a shipyard. And second generation goes block system. First generation is a loop system. Second generation is a semi-block system. Was installed on the reactor on this icebreaker and used to and give the Soviet maritime program significant experience in operation. It's the most powerful nuclear vessel, in civilian vessel at this time, and bunch of third generation of nuclear icebreaker was built. I personally was on the launch of a couple icebreakers on the Baltic shipyard, and I visited several of them as in a program just to make myself familiar with. And for example, I was on the Finnish built icebreaker timer when it was like reactor being installed. And a lot of my friends used to work on the icebreakers and as a chief mechanics or mechanical engineer, shift, like shift mechanics and so on. And what's interesting, on some point, Soviet Design Bureau changed the, like make some decreased level of security for the naval reactors and try to apply naval reactors with a huge experience and huge operational experience with some accidents and everything, like collecting some data and switch this information to the civilian, what actually not happened in the United States and still to be, like secret, even, like first reactors still to be in secret. And it's helped a lot. It was a huge jump to the development of a civilian pre-SMR and SMR program. Third generation is okay, second generation is a semi-block, third generation is a block. It's a reactor called KLT-40. It's pretty similar as a naval reactors, but it's a different core. And this reactor can operate in 20% of national circulation power, 20, but especially for submarines, for example. But it's a force, mostly it's operating on the force as a forced circulation system. But the core is different, and core is a K for the small modular reactors. And fourth generation is a kind of prototype of a written, but 100% of national circulation, no pumps.
Really?
Pretty much similar reactor as a written, but the Navy is very very careful about the operation with national circulation all time, especially because like such reactor has a free surface on the top, and during the rolling and pitching, like this surface is moving and it's creating unstable circulation in the reactor. And but by the way, for floating nuclear power plants, this works 100% perfect. And pretty much same reactor, and just installed couple pumps, and we got written 200, and in my opinion, is the best light water small modular reactor in the world right now. And Russia built these reactors. Like I try to check how much they building, like 2 or 3 or 4 reactors every year,
Yeah.
like making cookies. And was comparing, like, United States talking about reactor, Russia's just building reactors. It's not about the military, it's about the civilian icebreakers. Regards to, like this fantastic project, submerged natural gas tanker, we created reactors for such project 40 years ago already. Some of the guys who they, like when I was on the diploma project, my master degree diploma project, some of the guys developed something like reactors for such projects. What's good about this, like if you have submerged vessel or submarines, like you don't have, you require probably 30% of less power because you're missing one component of the power loss. It's like, like you have foreign losses when you move in vessel, you have surface losses, friction when you move in vessel, and you have waves losses. And waves losses, it's not applicable for a submerged vessel. What means, like you it's effectively, effectiveness of a propulsion system, like significantly higher, which means, like this is the reason why submarines so fast, like they can have like even 40 knots under speed under water. And it's not new for Russians program, but today technology was, like 40 and 30 and 20, even 10 years ago, technology was not so developed. And hundreds core was tested, and cores and fuel completely different than like any light water small modular reactor designed right now in the United States and around the world. And Russians not counting on uranium-2 fuel because there's a lot of disadvantages, especially it's caused problem for the naval reactors because required maneuverability, required load follow situation, and UO2 is not capable to to follow such fast maneuvers on the maritime projects. And this is a kind of background of situation. And regards to Arctic, like Russians considering the Arctic as a, like new base, Siberia and Arctic and Far East as a new base for state development. And I actually get one pretty interesting opinion from one of my friends in Russia. He said, "Oh, okay, we're gonna develop Arctic if something happened and war conflicts happened. Like Europe gonna be destroyed, some part of Russian territory gonna be destroyed, but we're gonna have place to start up the new country or new state if it's World War III happened." It is actually interesting opinion about it. But anyway, a lot of activities in Arctic right now, and yeah, and this is a situation.
As you mentioned, I look to China and Russia for sort of where Western fantasies go to come true, or at least where things seem to be several decades ahead. We've been living this SMR mania in the Western world over the last several decades. Promises of serial deployment of standardized reactors in factories, and we have yet to see a small modular reactor deployed. We do in my backyard have the BWRX 300 finally getting built, but very much stick built, and quite a large reactor. And we'll see how that goes. But again, from this perspective of building reactors in factories, building multiple standardized units, the RITM, or Rhythm, as I believe it's pronounced, reactor program. This is the last of the generation of icebreaker reactors that you just described. An integral pressurized water reactor, I guess with the steam generator and pressurizer inside the reactor pressure vessel. We saw that this is essentially similar to the new scale design, which again, that project fell through, unfortunately. And the Rhythm reactors, you said, are being rolled out several per year for the icebreaker fleet. I believe there's, I think, 8 planned for 4 further of the 22220 class of Russian icebreakers, but also projects in Uzbekistan, land-based projects in Uzbekistan and Yakutia, a northern region of Siberia, and also multiple floating nuclear power plants that are also going to use the RITM, or Rhythm reactor, to power the Bemskaya copper deposit, which is very close to where the academic Lomonosov is moored. So we're just seeing what looks to be the maturing 400 reactors of operation in this nuclear icebreaker program, culminating in a reactor that's probably still can always improve on something, but has reached a real level of maturity as a small modular reactor, and one to me that seems could be quite economical in that it's actually quite compact and quite simplified as an integral PWR. I'm really curious. I don't know much. I've described an integral PWR. That's about as much as I understand in terms of stuff that's usually on the outside being on the inside. But I'd love to hear a little bit more about, again, just focusing on the Rhythm and understanding, again, a little bit more about why this has been the reactor that's sort of been down selected and now being standardized in a number of both icebreaker, power barge, and land-based applications.
If we want to, like implement any project, we need to understand economical aspects, yes. And what I can say right now, I don't believe any economical calculation or any economical models in the, like presented in the United States or in like multiple conferences. First of all, because, like any single model not taking into account like multiple aspects of the SMR operation, Or for example, like, like as you mentioned, BWRX project, 20% less than, like conventional nuclear power plant. Yes, like size. Or okay,
Yeah.
how about a new scale? And I know this project and guys who used to work on this project. I used to work for them like 2 years, and actually I developed for them first, explained them how to reactors operate, and they used to work in Oregon State University in MASLAB project. And I told them, like guys, you thinking about like the cheap fuel, like you you too, like it's gonna help you to make reactor cheaper. No, it's not. It's not because like fuel cycle is different. Your peaking factor is different. You need to refuel all time. You fuel reliability is completely different than conventional nuclear power plant, which actually works on a steady state pretty much and very slow moving time to time. Like it's not works like this. It's not works. Just not work. And I told Jose Reyes in 2004, like believe me, you're gonna be change everything. And he said, no. I said, okay, it's the first two, 1, 2, 3, 4, you need to change. And they start to change 1, 2, 3, 4, and they, like except fuel right now, they change pretty much everything what I predicted. Because, like it's obvious if you know a little bit about. What happened with reactor like Reading? What's happened actually, how it was created? I think like Lightbridge American corporation, yes?
Yeah.
And this corporation was started like about like 30 years ago, and two Russians engineers from Kurchatov Institute immigrated to the United States and started and tried to clone Russian submarines and icebreaker reactor fuel. I met this fuel 40 years ago, first time.
Yeah.
It's like cruise. I call this X type, or like clever type. Uh, what's the difference between UO2 fuel and this fuel? I believe this is the best fuel in the world right now. What's the difference? UO2 has a very low thermal conductivity and very high heat capacity. If you take in this geometry plus intermetallic fuel, which actually uh, very well known, for example, in 60 years of operation in ATR. Yes, it's low temperature, but fuel meat is operated with a huge, like 90 something percent of enrichment. If you're gonna take this fuel, like intermetallic, like uranium and aluminum plus silicon, you can create thermal conductivity probably over 20, I think over 20 times higher, which means the temperature in the fuel can be significantly less than the temperature in the UO2 inside. Which means, simple equation, if you calculate gas pressure inside conventional fuel UO2, which actually 3, for example, times higher than in this fuel, your gas temperature is 3 times higher and pressure is 3 times higher. The biggest problem for the fuel not is like high burn up. Biggest problem for the fuel is a high pressure inside the fuel element and fuel pin. And if your fuel pin has like 3 times less fuel pressure, gas pressure inside, you can burn this fuel more and more and more, right? It's a
Okay.
simple engineering understanding. If you have small core for a small modular reactor like 66 or 69 fuel, I don't know, fuel assemblies like SMR 300, whole tech, by the way, ridiculous design and never gonna be built. New scale, 66 something fuel assemblies. It's a small core, a relatively small core with a standard configuration on fuel assembly. Peaking factor for small core every time higher, which means in the peak of the temperature of the flux is higher, which means like this specific point is more like heated more in the specific points of the core, which means, like temperature in this specific point higher and pressure in the fuel assembly, in the fuel pin is higher, which means, like it's required to reload it faster,
Right.
more often. What means cycle is non-economical. The, let's call this light bridge fuel is completely different. And it's, like you have significantly higher core life cycle. This is the first component. Like light bridge just take the Russian fuel and trying to make clone. Actually, they trying to make clone back 30 years. No success yet. And core for readiness is not so small. Core for readiness reactor is like about like 1.5 meters compared to like, it's 1.5 meters and fuel pins is smaller. It's like, like it's a piece of art, not a core, And if core has a, like you can load less fuel, you can have long cycle, you can operate differently, like, and, like Texas A&M University right now testing like this twisted cross type fuel for a light bridge contract. They tested this already. And they have special center of small modular reactor. They have test facility. And it's the first component of the reactor. Okay, you have, let's say this way, higher thermal pump instead of the, like heavy, low, like hard, not good operating, with not with a fuel, with a old fuel, actually 40 years old fuel, less reliable, heavy to operate, and like less efficient. Natural circulation pump part of the circuit. It's one component. Okay, second component. For example, core of the, like Rolls-Royce reactor is relatively small, but has like about, I don't know, 20 or 40 control rod drives. Core of a rhythm has just 7 or 8, which means, like it's operating completely different. Which means, like it's already big step. Absorbers is different. For example, if you're using europium, maybe more expensive from one point of view, but europium has a long chain of isotopes, pretty much same absorption cross sections. It can be operated decades without any changes. And the next step is a riser or chimney, big chimney, overflow, and steam generator. It's pretty funny. Like if you can see, new scale steam generator is a huge machine with 1,500 tubes. Like it's a how many weldings on this? How many? How reliable is such machine? Like it's like how big is this? And actually, it's a coil, yes. And compared to, for example, rhythm steam generator is actually has a straight pipe, one screw steam generator, but it don't have
Yeah.
any welds in between. Like it's about like 2 meters only. And all these components, including some specific aspects of the how we call this self-containing gas pressure, built-in gas pressurizer, which actually give you opportunity to capability to maintain floating, I call it floating steam, floating pressure in the primary side. For example, nominal pressure on 100% of the power, but it's a lower pressure of the operation. It is floating or adjusting all time, which actually give you opportunity to operate much more flexible. And finally, compared to new scale or AP300, readiness has like about 3-4 times shorter. Another aspects of a designer is in small, compact. You cannot put the new scale machine or something else on the barge or vessel. It's a huge. It's an ice
So
scraper.
tall.
It's an ice scraper. Heavy,
Yeah.
huge. But another aspects, the people not thinking about this sometimes, like I mentioned the economical aspects. Each core can be calculated for the one parameter, equalized by one parameter. It's a power density. If your power density is small, you need a big core to get same power by volume. If you make a big core, you making the big vessel, you making big biological shielding, you making big reactor compartment, you making big reactor protective shell or something like this. You're gonna build huge machine, huge. Which means, like people not think about like, okay, we're gonna build something. How are you gonna build something? You whole is your vessel sink. Like if you're gonna put such machine on this, and uh, like, and when I started to think about like officially think, not in my side, like an ABS, for example, I used to work for ABS, and I was I was like I did ask, like you develop this, you develop this, you develop this, guys. How you and think about like you don't have like technical requirements. What kind of cover damage should you have? What kind of double bottom you should have? What kind of like did you ever think about this? No. How you gonna be like, classified? Like oh we're gonna make this, and like and from this kind of aspects, I start thinking, okay, guys don't thinking about the maritime condition of operations. And
Yeah.
I start asking, and actually I developed my own and actually trying to implement this definition of maritime condition of operations. It's taken into account severe storm, pitching, rolling, and if you, for example, you you maritime nuclear object sink, is it sink on the even keel or is sink like this or sink like this? What happened?
Right.
Even control rod drive machine should be designed like this. If you think turn moving out from core, what happened?
Wow. Yeah.
People not
Yeah.
even think about this.
People don't think about upside down reactors unless they're designing for.
Now it's a maritime operations.
Yeah.
You should
Yeah.
think about this. You should think about what's the requirement for the control rod drive. What's requirement for the core? What's the loading? What's the dynamic situation? And it's a maritime conditions.
And this would be a design, like when we talk about sort of beyond design-based accident, like a design-based accident should be your reactor doing a 180, being upside down.
Yes, it's also
That's conceivable in the ocean.
yes,
Yeah.
again, yeah, true. Like it's a situation, and like but. I tried to talk about this with a core power, for example, and I wrote like several articles about this, like white papers about the like maritime operating condition, technical requirements for maritime reactors, uh, uh, roadmap for the maritime reactor development, situational awareness for the maritime operation. Because like one situation when reactor on the sea on the vessel, and our when reactor on the like on the port, and it's a different story. Yes, it's a one is a it's all time emergency planning zone is a dynamic. It should be changed. Uh, uh, it's significant problem. And when people say, okay, we're gonna build maritime reactors, I say, okay, guys, good luck. Good luck, build it, and like, and you're gonna do this. And another part of the story, I'm immediately start think about like technology readiness. Because like
Yes.
the people
Yes.
say, okay, we're gonna build molten salt reactor. Okay, guys, do you have like is your port ready? Do you know anything about the waste management for this molten salts for the land-based reactor, not even for the maritime reactors. How you gonna do it? How you gonna be operate this? Like how you gonna think about this? And I, like spend time and develop like special tables for technology readiness level analysis for fuel readiness level. I trying to present it everything and like share it to community. It's a big deal. You should think about everything. Like you cannot think about like, okay, we're gonna create core. Okay, what's core? Core is the core. Like, and people from core can be calculated to the guys who just graduated from university, and if you're gonna give them, like correct geometry. But like you need to operate whole machine from core to propeller. And people not thinking, like in the complexity of the system. Navy, yes, Navy can do this. But US Navy is very secret, and they, as I mentioned, they not even open information about the first generation of reactors. Russian is open information about the first, second generation, or even third generation reactor, partially.
This whole question of lineage is fascinating. Exactly what you're saying there. The first Russian nuclear submarine IP is made public, at least for the icebreaker fleet. The icebreaker fleet develops it further, goes through multiple generations. We've arrived at the Rhythm, and now an even larger Rhythm 400, which I believe will have 100 megawatt electric output. So we're getting into a pretty respectable size for an SMR, and now that is being deployed in power barges and even land-based applications. So I think what that speaks to is a kind of maturity and maturation of a technology, and debugging and sorting out response to failure modes and fuel failures, as you're mentioning, improvements in fuel, accidents even, and arriving at a mature technology. And I think in the West, there's just this idea that, we can just make cell phones of nuclear and leapfrog landlines. And it's just that easy without understanding the battle testing that's required for this technology. And again, technology readiness level, did it have a high technology readiness level on a Russian nuclear submarine in the 60s? Pretty high technology readiness level, but I feel like we should get into 9 plus plus in terms of thinking about, again, just all the battle testing that these reactors have undergone, which I think in comparison really makes some of these, molten salt reactor based marine applications just absolutely fantastical. I mean, never left a national lab, a couple of reactors of operation, very buggy, under Alvin Weinberg. This is not a mature technology.
I'm gonna send you couple of my articles to see this. And if we're talking about technology readiness level, yes, I already mentioned the fuel is a core. It's a core itself, and fuel is a key component for a reactor. And let's put this aside. But like if we're talking about the technology readiness, for example, and we understand, for example, like like we have several like 4 or 5 general technologies with some branches like high temperature gas reactor compared to gas reactor, gas cooled reactor, and so on. We know fiasco of the gas cooled reactors in the like for a large conventional nuclear power plants, yes. And we understand, like people say, okay, we're gonna make, Brighton cycle, so on, and we're gonna have very efficiency. Guys, like you're gonna make Brighton cycle. It's great, like, but expenses of with Brighton cycles and this like jubilee level of the machine is gonna be so expensive compared to, like Rankine cycle, just regular gas cool system. Like it's no advantages here. Or for example, let's say, like lead bismuth or sodium reactors, like lead bismuth or lead, like lead is a very well known reactors, at least in Russia, like sodium, like great experience again in Russia. Like people who used to work on the ABR2 or ABR1, already, like very far from, retirement. Like it's possible to create and recreate. I understand this. But based on the technology analysis, is a simple conclusion. The only light water reactor can be, significant step with the SMR development on the next 10 years, 15, or even 20 years. Because no any single reactor right now has like normal test facility. They're gonna be built critical, like zero power level, but critical, and again and again and again and again. And people say, okay, we're gonna do TRISA fuel. Okay, TRISA fuel is 40 times more expensive than regular fuel. 40 times. Yes, it's give you significantly more better burn up, but it's again, this is remember power density in the core. TRISA give you like very small power density. Heat pipe reactor multiply this, like getting lower again. You have, like for micro reactor, you may have huge machine as a micro reactor.
Yes. Yeah.
And we're
Yeah.
gonna tell,
We
okay,
see
we're
we
gonna
see that
build,
with the Vinci. Yeah.
we're gonna build heat pipe reactor and they're gonna be transportable. No, guys, it's not gonna be transportable. Try to, I'm asking all the time. And people so disappointed my position. I said, okay, guys, good luck. You know, like, like if somebody say, oh, we're gonna build like a reactor with a fuel with a coolant cubic meter price like $2 million. One of the company building like $2 million. Come on, like $2 million for cubic meter, and you're gonna be clean all time. This and it's like people not think about this. This is a problem. This is not a problem to develop technology. Problem to think about everything at the same time.
And to make it economic. Yeah.
Yeah, and make economic is absolutely like you guys say, okay, we're gonna build reactor for $7. Come on, $7. Like you don't have any data to to understanding to build it.
Yeah. Just to drill in a little bit more on this idea of an integral pressurized water reactor. Again, that was what I had understood as when I was kind of new to looking into this area. I thought NuScale was sort of revolutionary as the kind of leader to first ever to make an integral pressurized water reactor. That was my ignorance. Obviously, these have been deployed in the past, I believe, on submarines. I think the Otto Hahn, the West German nuclear cargo vessel, was a Babcock and Wilcox integral pressurized water reactor. So these have been done before. What are some of the advantages and disadvantages? Just to my non-engineering eyes, it seems like maintenance of a steam generator inside of a reactor pressure vessel seems challenging. Just how do you shrink something down and still get good efficiencies out of it and cram it into a reactor pressure vessel? I think the pumps are sort of on the outside, or there's natural circulation. Just can you demystify the integral pressurized water reactor? There's hype. We hear about the Koreans building one. We do have it in operation in the Rhythm. So help us understand better again what is an integral pressurized water reactor and the pluses and minuses.
First concept of the integral pressurized light water reactor was published probably in 1961 in the United States. I don't remember how it calls SNGP, something like this. Several concepts were presented in this document, and Octagon is a very typical project, and actually is pretty good project. Just only like even today you can use this as a modern reactor, just replace a core, for example. That's it. And it's very interesting and very, like significantly more mature project compared to any, Haltech or NuScale or Rolls-Royce.
Sorry, this is which reactor?
Octagon, which actually built an Octagon vessel.
Oh, Otto Hahn. Yeah, the Otto Hahn. Okay, got you. Yeah. The Otto Hahn PWR on board the West German cargo ship. Yeah.
It's well-known concept actually. Like the Rhythm compared to Octagon, like Russians designers all time think, okay, no any small hole below the core level. What's Octagon, like you have kind of two pumps built it on the pipes, like coaxial pipes, and connected to the bottom of the reactor. Russian never did.
Yeah.
Russian all time the core should be, below the any holes. Such reactors, such type of reactors has a significantly less holes in the vessel. And two different aspects, again, two different paradigms. For example, compared to NuScale, I call this Western safety paradigm and Eastern safety paradigm. The American or conventional nuclear power plants always has a pressure relief valves, and if you shut down the reactor, if something happened, you need to open the pressure relief valves and drain steam from a vessel, cooling the fuel. The Russian and this system transferred to a NuScale, for example, and transferred to a Holtec, for example, and so on and so on. Russians thinking differently. Never open the reactor. Keep water inside. Give them, make the circulation inside, and move the heat from reactor vessel different way.
Yeah.
First way required significant, big safety systems. Second way required reliable but unified safety systems and relatively small. If you're using uranium-2 fuel, it's required. It's the whole idea of the modern Western SMR based on the conventional nuclear power plant system, and they're trying to make the conventional nuclear power plant smaller. The Russians doing different way. Russians doing this, make it smaller. And if we compare number of holes or any pipes connected to the reactor, for example, in NuScale, it's something like about 20 to 30. Ripon is a 5 only. Small. I'm not talking about feed water or steam. I'm talking about generally, they have significant number of pipes. If you have significant number of connections to the reactor vessel, you have significantly higher probability of a locker.
Yeah.
Yes? And what
Yep.
happened with NuScale? They don't defend the opinion or the emergency planning zone, small emergency planning zone in NRC, because they don't accept, this idea of, we don't have locker. You have locker. But if you have several small holes only, 1 inch, it's it, or if you have several 6 or 7 inch holes for connecting to a cooling system and moving cord. Steam generator as I said, is a second key component. If you have steam generator like in NuScale, the huge with 1,500 pipes, lot of welding, and you cannot use this for cooling. Just for regular cooling, yes, but not for the emergency cooling. Because
Yeah.
water hammer or time happened, you can just broke welding and that's it. It's a big deal in the design. It's a question of paradigm, how you thinking and how you creating the system. By the way, I start to do this and create my own monograph how to build small modular reactor, 650 pages of explanation why you making this decision, it's a big deal. And I was surprised. No any single university in the United States present this course for teaching for a student. Yes, they present in course how to calculate reactor, how to do neutronics, how to do thermohydraulics, but nobody teaching students how to invent and design the machine. We did this in my life. Actually, we did this in school, in university, one by one, step by step. Core, steam generator, how it put all together, pump, pressurizer, how they put it and presented each time, each semester, and finalizing this over 6 years. No such course in the United States, and it was surprised for me.
Can you just explain to me in a bit more detail, because I think this is really key. In the Western reactors, lots of perforations. Your I guess pressure relief. You're letting excess steam off in order to handle accident scenarios. And you mentioned in the Russian ones, minimal perforations, and you're just trying to transport coolant, I guess.
Yes,
Just
coolant.
help
Yes,
me understand that a bit. Yeah.
yes, and because they have different steam generator type with very low pressure loss in steam generator. We connected steam generator to a special heat exchanger outside of like, okay, you have steam generator inside the reactor. You connected feed water, you connected steam, and you moving steam out. Yes, and if you connect to a feed water line and steam line, you connected additional heat exchanger, which actually, and this heat exchanger disconnected during the normal operation, you just operating normally. But if something happened, um, valves on the steam line closing, valve on the feed water pump closing slow because the feed water, you feel steam generator more, and it's closing also, but valves on the additional heat exchanger, let's say, which actually recommend during the accident, opening on the steam and opening on the water, and national circulation circuit organized through this. If you have huge, what national circulation required low pressure loss.
Yeah.
If you have steam generator like new scale, huge, if you long tubing, like, and so on and so on and so on, this steam generator has a huge pressure loss, and you cannot organize such circulation. You're using the, like, additional reactor protected shell, not, let's say, shell or no compartment, which fill water and so on and so on and so on. And you creating, like, biggest water pond in the world to keep
Yeah.
this reactor for operation. You know,
Yeah.
and this is completely different story. We wrote one article with a professor here, and we present this small piece of such system in this article. And in my project, I developed, like, this system, in details, and it's a different story. Again, different paradigm for the design. We cannot, like, explain everything, like, in one podcast, but it's a little bit different understanding.
Sure. I guess we're gonna have to wrap up soon, but uh, in terms of some of the considerations that go into a maritime reactor, you mentioned sort of the pitch and roll. There's also the potential for impacting with another vessel. I mean, it sounds like just an incredibly complex set of scenarios to plan for and resulting design philosophy. So, I guess speaking to myself and probably an audience that's sort of less familiar with putting reactors on boats and some of the challenges, biologic shielding, etc. What are some of the key things that you think people probably aren't considering or missing or just not appreciating because of just a lack of familiarity with this area?
Hard to say,
There's probably a lot.
yeah. Um, what I see, like, in the any companies where I used to work, like, if I have colleagues who used to be in, Russian Navy, American Navy, they understand situation completely different. They well educated, well known, has a well experience in this, but they not participating a lot on the projects. Like, I don't know, like, what's difference. Like, the biggest difference for me, like, people, like, you trying to explain why it should be like this, and they say, okay, we know, we all know, it's I'm usually say, okay, like, good luck, buddy. Like, if you know. The problem is right now for American, nuclear industry, we have brave. lot of smart guys, but these guys very young, and they think, okay, we're gonna do everything. We're gonna write script. The script's gonna calculate everything. We're gonna use AI. It's gonna do, like uh, I don't know, hard to say. I don't want to criticize a lot, but like it's hard to say. Okay, sometimes I say, okay, the last like 40 years ago we built reactor, and we have like in the reactor design team we have guys who's operated reactors, who's actually see how to operate. Like 20 years ago we built reactors, and we actually has people who knows the guys who operate reactors. Like, like right now we actually don't have in the reactor design team guys who actually even see reactor in life.
Right.
I give you a simple example. It happened like several years ago. We met like, like about 40, 45 people sit in one room, and they, like, it was like team building. We're doing, like we're great. We developing new reactor, blah, 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 blah. And in the end, like one guy asking me, do you want to ask something? Our, huge group. I said, okay, guys, like 45 kids here. Who is you like ever see reactor in real life? Just only one,
Oh my God.
except me.
This was a nuclear engineering class, or?
No, it's a nuclear engineering development startup.
Oh my God.
Only one.
Oh my God. So to contrast that again, because this is, I think, a big takeaway that I want to try and illustrate for the listeners, is again the sort of ecosystem in Russia. Just looking at the Afrikantov OKB Design Bureau, I understand there's 4,000 employees. It's been around for something 70, 80 years. You mentioned your father crewed or worked on the Lenin icebreaker. Just the kind of the richness of an ecosystem in which there's people with entire careers who, again, not just are dreaming up reactors, have seen them, have built them, have operated them, have dealt with accidents and issues that have arisen, have hundreds of colleagues like that, where there's young people joining in, but there's people with many, many years of experience. There's not been a 30-year gap as there has in a lot of the West, where we just haven't built anything, or where no one has run a sodium fast reactor since 1994, for instance. I just want to get a sense of almost like what it's like to be within that kind of a design bureau, whatever environment that you were in, and just contrasting that with, again, I mean, you've just kind of done it beautifully for us, 45 people at a team building exercise, designing a nuclear reactor, and only one of them's ever actually seen an operating nuclear reactor. Like, this is almost like an anthropology exercise here, right?
Historically, Soviet Union has a lot of different design bureau, like, especially, for example, for like Nevskaya or Severnaya, or like Malachit, Rubin, so on and so on. They built like naval and maritime ships and vessels. Yes. Uh, Regards to Afrikantov, yes, they have several thousand people, but Afrikantov not only like design bureau of the reactors. Afrikantov doing a lot of different stuff. And in parallel, they not developing one project. They probably same time developing 10 different reactors, including,
Right.
for example, reactor for Poseidon, like a nuclear torpedo, for example. They developing in the same time. You're talking about like a 4,000 people, but some people developing new steam generators or something like this. Some people developing something else. Some people developing something else. This is a like huge organization which actually not developing only one reactor.
And is this like a central campus? Is this sort of like, when we talk about the Afrikantov Design Bureau, is it a physical location, or is it?
Yes, it's a physical location in the Gorky and Nizhny Novgorod right now, and it's a lot of like very smart people. I have actually several books with autograph of authors about the operation, and the academics and professors from Afrikantov. in my library.
So to do like a compare contrast, like I just got back from a tour of Canadian nuclear laboratories up at Chalk River. This is the Canadian sort of hotbed of nuclear research. Right after World War II, it was the second largest nuclear research center. We had one of the most powerful research reactors in the world, NRX, NRU. Right now, it is operating a very, very small, calling it a research reactor. I think it's just several kilowatts of thermal capacity, a tiny little neutron source. That's the only reactor that's operating at this facility now. 60-70% of the budget is in decommissioning old buildings. There's some interesting research going on. I really don't want to knock it. It was a fantastic tour. I got to meet some great people, great biologic research, interesting machine shop, building things for the Canadian nuclear industry. But when I hear you describe, the African Tough Design Bureau, 4,000 people working on 10 different kinds of reactors, steam generators, everything else, like the degree of busyness and the degree of sort of human capacity that's built through actually, building projects, like it's a stark contrast.
Yes, maybe yes. Like African have more design and technical and engineering structure. Is even if I used to work, I'm not, like I operated the product, but I'm not very close
Right.
to them. I was,
Yeah.
but also several institutes, research institutes like Liponsky, for example, and in Obninsk, or or even NIT, where I used to work after school. And it's a test facility. They test facility. They develop in different real tests from the real reactors. Of course, like today, the coding and the calculations with actually proper benchmarking can help you a lot. And what else good for light water reactors facilities or for small modular reactors is practically everything known about it. Practically, like if you compare any startup on the different technology, was probably required like 75% of research, and maybe just 10% research required for light water reactors for specific design system. But
Right.
like science research is a huge and very expensive for any other reactors, any other
Yes.
technologies.
And what you're saying is so much of that has been done for pressurized water reactors already. You're
Already,
building on top of,
yes,
yeah. Versus if you're going to be working with liquid metals or highly corrosive, high temperature molten salts, there's a lot of basic science that needs to be done to figure out the alloys and things like that to make this work. And science also isn't commercial per se, right? I mean, the kind of science that leads into the deployment of a commercial product decades away, this is a big investment. Usually this is a state investment, not a private startup that's going to sort this out and make a pile of money for its investors.
yes. For example, if we're talking about like core power, yes, it's not a big company, like 2 or 3 guys, nuclear engineers only. What we can do? They just can create library for calculations. We create like small understanding of the core and try to calculate this, and that's it. Make a model and nothing more. They have good. Maybe they have good capability for the calculations, and they have access to the code, and even they have talented boys who can create models. But like you require tests. Where can you do this? And how can you do this? This Kairos power in this case is much better condition because we have a lot of money and they have a lot of test facilities.
Yeah, yeah,
But they design and they can sell information to others. And if you have, let's say, like 30 project in United States, for example, and let's say it's even like average couple hundred people in each project, average, yes,
yeah.
is a 6,000 people compared to Africantov 4,000 people.
Right, right. Working under one roof in a coordinated fashion,
Yes,
pulling on the oars, and the boat's going in the same direction.
yes, and it's very rough calculations, but it's give you understanding. Like okay, it's not no, and also Russia has like Mikiet or something else, like it's a smaller who is working on the conventional nuclear power plants only, but they also developing small reactors, like trying to develop small reactors, like they call this ISMR, like they trying to move same way like NewScale and say, okay, guys, forgot about this. So somebody trying to, say, okay, because
Right.
NewScale is so popular it last, like
Right.
10,
Right.
15 years. But it was so predictable to fiasco.
Aleksey, we've got to leave it somewhere. This has been a fascinating conversation. I credit the miracle of LinkedIn and WhatsApp with many meetings with great people and the building of a fantastic network. I'm really grateful to be connected with you, and I look forward to more conversations in the future.
Okay, good luck. Thank you. Thank you for conversation.
Today's episode was made possible through a generous donation from the Xerxes Foundation and from listeners like you making pledges on our Substack. If you'd like to join the tribe, please do head over to our Substack, smash that pledge button, or if you would like a tax-deductible receipt, you can hit the donate button and make a contribution through our fiscal sponsor. We genuinely appreciate your support. It is only through your generosity that we are able to continue to offer energy literacy on demand.